I would like to introduce Robbie. Robbie is a tech lead on the Google Cloud AI platform and one of the founding members of the team. He built the first TensorFlow backend of cloud machine learning engine service, and currently he's focused on ML prediction and related services, likes to work on other areas of machine learning and cloud platform. Before his time at Google, he studied statistical natural language processing, culminating in a dissertation in the area of machine learning known as active learning. Robbie, in his outside work time, likes to spend time with his kids. He has 5 lovely kids, and he's very passionate about that. I've known Robbie for the last 2.5 years, and you couldn't have been in more better hands than Robbie. So Robbie, please take it away.
All right, thanks for that introduction, Puneet. My name's Robbie Haertel, like he said, and I'm really excited to be here. Just by way of, I know you're going to fill out, we keep saying, hey, we want feedback, blah, 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 blah. A couple questions along that line. Just informally, how many here would consider their role to be a data scientist, their primary role at their company? That's a good number, but might not even be half or just over half. What about data engineer? Do you consider that? Some of the same hands went up. If you told me before, I would have chosen the other one, right? You got some data engineers. What about just like software engineer? That's a good lot of people. So those that are software engineers, are you here because like machine learning is maybe a hobby or something that you're looking to get into so you can go down that path in your career? Is that why you're here? Anyone here for other reasons? Just because of pizza? Someone here for the pizza? That's why I came. They said, you can have free pizza, but you got to give a talk. I said, worth it. So here we are. You're doing a startup. Yeah. And so you're here to figure out what's on offer for that, right?
Yes. Yeah.
Very cool.
Can you show us how to implement Google Duplex?
Well, speaking of that, let's set expectations. So as was mentioned, I'm one of the leads on the Cloud AI platform team, right? So our job is to provide a platform for you guys to do machine learning. So if you came here thinking that I'm going to show you how to train really fancy models to get the highest accuracy, and here's the tricks you do in Scikit-learn, and here's the hyperparameters you tweak in XGBoost, you're probably not at the right talk. I hope you'll stay anyways. But what I'm here to show you is what the Cloud AI platform, are you seeing like all my emails come up and stuff? What the Cloud AI platform can do for you folks in your roles, either as a hobbyist trying to learn, as a data scientist trying to get your job done, as a startup. I think Cloud has a lot of benefits for startups, actually. How many here would consider yourself to be working for a startup? I'll raise my hand. You're like, what? Google's not a startup. But Cloud AI platform, this is a relatively new area. I know that they have existed. Google, actually, I worked for an internship at Google for what was known as the Prediction API. We recently turned that down. But that was one of the first public cloud machine learning offerings. And I was actually sad to see it turned down, not just because I worked on it. I think it was actually ahead of its time quite a bit. And it's still probably ahead of its time. We still probably have a few more years to go until we can really realize the promise of here's a CSV, here's your trained model, go for it, right? But anyways, thank you for entertaining that, and thank you, Puneet, for setting this up. I'd like to think that I was capable of doing that myself. As I begin here, a special thanks to people that helped me with the slides and the demos that are here. I couldn't have put it together without the following people: Noah Negri, Young-Hee Kwan, Bhupesh Chandra, Kathy Tang, who's in the audience right now, and the rest of the Cloud AI platform team. So I really appreciate all the help they gave me with the demos and stuff. And then, of course, special thanks to those that organized this meeting, and special thanks to all of you that are attending. Back to the topic of providing feedback. I think Puneet mentioned that Cloud AI platform started about 3 years ago. So we do have some experience with working with users, with getting their needs and requirements and trying to understand those. That said, we believe that we're at the very beginning stages and that there's so much more that we can and should do. And in fact, we believe that we're in a hypothesis testing phase, right? And what we would like to do is we've made certain assumptions. And as we go through this talk with you, if you notice some assumptions that we made that are wrong, I'd like you to come up to one of us afterwards and say, hey, what about this? Did you think of this way? Or hey, you know what? Our requirements are actually a little bit different. Have you thought about providing this? And we'd really like to understand those things, because if we build a platform that you can't use, I've just wasted the last 3 years of my life. And I'd like to think that I was trying to do something useful. And even if I failed the last 3 years, I'd like to continue on this path of building something that you guys can use. So the topic of the talk, as has been mentioned, is, well, I kind of changed the topic slightly, but it's production, Scikit-learn, and XGBoost. Specifically in the cloud. We'll talk just briefly about off-the-cloud use cases. But you guys are, most of you here, about half of you said you're data scientists. Some of you are hobbyists or did ML in grad school. So you're very familiar with this. Is my mic still on? I feel like it went off. We're still good? OK. You guys could probably preach to me about this. This is my view. I won't spend a lot of time on it because I believe you're all familiar with it. The model development cycle is more or less like this. You have a problem to solve. You collect data that will help you solve that problem. You almost always have to clean the data. Then you decide what model you want to use. If it's an image classification or some sort of perception problem, audio, maybe some text, you might use a neural network. But if it's click-through rate prediction, you might use logistic regression. If it's structured learning, maybe you'll use gradient-boosted decision tree, something to that effect. Those of you that have been in the field long enough kind of already know this type of problem. This model works well with this type of problem. Then you need to go through and take this raw data that you've cleaned and analyzed and collected, and you need to do some feature engineering. Especially if it's logistic regression or some sort of linear model, you're going to need possibly quantization, one-hot encoding. You're going to need to do feature crosses, all sorts of things, logs of certain types of features, all those types of things, right? And once you've done that, you can now take your data set and you can train a model. And most models have hyperparameters. And your goal is not to get a model, it's to get the best possible model given the model selection and the feature set. So you'll train it, you'll do some hyperparameter tuning, and at the end of the day you have a model. And you'll take that model and you'll analyze the results. Hey, what's this model doing well? Where does it succeed? Where does it fail? And what can I do to get a better model out of it? And depending on what the errors are that you say, you may decide, I didn't have enough data, or my data wasn't clean enough, or my features, I need to add more features or different features. Or maybe I need a new model, a different model class altogether. Anyways, you go through this feature engineering cycle or model development cycle, and then what? You end up with a model, right? You have a model laying on your disk. Now what? So training a model is simply a means to an end. It's not an end in and of itself. We train models because we want to do something interesting. The problem is, let me see how many of you can relate to this tweet. The story of enterprise machine learning. It took me 3 weeks to develop the model. That's not too bad. That's probably about right. She's probably skipping how long it took to get the data ready. But we'll spot her that one. It's been over 11 months, and it's still not deployed. How many of you guys can relate to this? Maybe instead of 11 months, it's 6 months. Maybe it's 20 months. But at any rate, ignoring the data part, because we all know that that's hard. Very hard oftentimes. But getting the model into production actually takes often much longer than training the model. And how many of you think that the fun part is getting a model into production? My guess is that the reason you're here is because the fun part is making the model. All right? So what if you could take, this is a screenshot, and it's very hard to see, of a Jupyter notebook. What if you could take your code that you ran to train the model and click a button, and you're serving your model in production? Well, I'm here to tell you, obviously, that you can. And yes, I'm running a Jupyter notebook on a Pixelbook. So that's a plug for those that want to run Chromebooks here. What I'm going to show you here is the running example that I'm going to use is to train a click-through model. A click-through rate prediction model. And I'm going to use XGBoost as the underlying learner, and I'm going to use some Scikit-learn pipelines. Again, if you came to see some secret sauce on how to do this, you're going to be sorely, sorely disappointed, because you guys are going to come back and say, why didn't you do this? Why didn't you do that? Why didn't you do this? And in fact, I hope you will, because these examples are going to be in GitHub. Go ahead and augment them to your heart's desire, and we'll accept reasonable submissions in that sense. The training data that we're using is the Curtail sample, right? That's I think it's 11 gigabytes, and it's 7 days worth of click-through data that's publicly available. It was used in a Kaggle challenge. So if you look at the code here, we're just doing very standard stuff. I tried to keep the example overly simple for the sake of illustration. We parse a few arguments, and just because they'll show up again, I don't want to spend too much time here. Base directory is just sort of so you know where the logs are, and so you know where to export the model and that type of thing. And then the event date is what I'm going to do is given a date, I'm going to look back for 7 days, use the past 7 days to train a new model, and then go from there. Okay? So this here is like cheating, I guess. Max samples is 7,000. Recall that I'm on a Pixel book. I'm not going to be able to train on 7 days worth of data, and I'm going to emphasize that point on purpose a little bit later. This little block, beautiful block of code is just reading in the data, and you're like, why aren't you using pandas? I won't get into those details, but there is a reason. It's to get the right data format so we can use a dict vectorizer. Here's the XGBoost regressor. I'm training a XGBoost model, obviously, for binary. It's kind of like logistic regression, I suppose. And then we create an Scikit-learn pipeline where we have a dictionary vectorizer, which will turn the categorical features, do the one-hot encoding for us. I call pipeline.fit. We cross our fingers that it works. And we won't necessarily wait for it to finish, but it won't take very long because I used so little data and all that stuff. It says it's done. So with essentially one line of code, you save the model out. I'm sure you guys are all familiar with how to pickle a model. And then this command here, gsutil, is just a file copy command that you use to go to the cloud, because if you try to use CP, obviously won't know how to get it to the cloud. So we saved the model, we copied it to the cloud. Now we need to actually deploy the model to us as a service on the cloud. What we're going to do is with these commands, these two commands here, is that's going to create a REST API for you that you can then send prediction requests to, and it does all the load balancing, it does all the auto scaling, it has the web server, authentication, authorization, prediction, etc. We'll talk more about that, although I might condense that part of the slides anyways in a few minutes. So this first line here, we have a notion in the current service called a model, which is essentially a collection of versions. It allows you to, and we'll see how this, in the context of training new models every day, how it allows you to keep various versions and switch between them. Like, I'm serving yesterday's model, and I now need to serve today's model. But for the time being, think of it as a container. We create this model. If I do it again, I'll get an error, because they have to be unique, so I'm not going to run it. Now, this mess that is curl will not be there in about a week or two. We just got the command line tool updated to accept framework as a command, and it wasn't there. So it's essentially, it's very similar to the models create command, but it's versions create. So we're saying create a version of this model. And since I bumped up the version to v4, when I run this, it's actually going to the cloud. And you can imagine, because it's doing all the things I talked about, load balancing, web servers, blah, 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 it does take a little while. But ours is actually very fast. It takes about, I think the median time is 90 seconds. Your very first model may have a little bit more in it time and be more on the order of 5 minutes, but it takes about a minute and a half. So while we're doing that, let's switch back to the slide deck. Now I know we have to do a context switch. For those that are engineers, software engineers, you'll understand that reference. But the question, why is production such a long pull? Remember, that was one of the pain points that we're addressing in this talk, is that it's hard to get models to production. I wanted to open that question up to you guys. What are some of the reasons that it takes so long for models to get into production in your experience? Getting the data? Well, what about once you have the model, though? So you got the data, you trained the model. All you really want is to show impact, right? To get better performance review scores or something like that. Validation? Well, that's a good point, actually. Yeah. And I don't talk too much. I hint at that on one of the slides, but you're not going to push something to production that's junky, right? Bring down your system. Any other reasons?
Yeah, performance evaluation.
Performance evaluation, absolutely.
Usually also you want to be sure that you can roll back if something goes wrong.
Yeah?
So you have to prepare for that as well.
Yeah, you got to be able to do a safe rollback. Very good. Back here?
Managing the infrastructure to handle the requests.
Yeah. How many of you like to do that? How many of you consider your favorite thing to do is to manage infrastructure? And that's why I have a job here, right? Doing this exactly. I may be the only one in the room. Here's a few other things. You guys said some really great things. I didn't even think very hard about this, and these are the ones that came off the tip of my tongue or fingers. You need to get approvals. You need to do capacity planning. Some people, I actually had a conversation, I can't recall right now who it is, but you have to convert your model from one format to another format and then do validation on it, that type of thing. There's some technical challenges. Somebody mentioned that just creating a serving system is a very complex stack. You have your load balancing, you have your web server, you have authentication, you have authorization, oftentimes you have a cache, you have logging agents, you have monitoring agents. They all have to work together. If you put all these, one thing is to get all those up, another thing is to keep all of them up, right? Because if any one of those pieces goes down, it's your pager that goes off if you're the production engineer, right? And you probably don't want that to happen. And certainly those of you that are data scientists, even if you're capable of doing this, that's probably the last thing on earth you'd want to do. Otherwise, you would be a production engineer and not a data scientist. So here's what Cloud ML Engine Prediction offers. It's click to deploy. It has auto-scaling, horizontal auto-scaling. So as you send up more traffic, it scales up. You send up less traffic, it scales down. And it's serverless, so it scales all the way down to 0, which is really fantastic when you're, like, for, say you're a startup and your traffic patterns are very sparse at the beginning phases, right? You get some traffic and you're happy, it scales down really low and you're not so happy. Or very spiky traffic, we scale up very quickly. Our servers are able to scale up very world-class, really. We give you encryption, authentication, authorization, logging, monitoring. You can organize your models with labels. You can do versioning rollouts and things of that nature. So let us go back here. Because it's a Jupyter Notebook, you don't get the nice spinny indicator. I don't have a nice extension to do that. But we can go ahead and just start sending traffic to it. So you can see that this piece of code is really boils down to these 4 lines, which is essentially one line that I broke up because lots of lines, a really long line is hard to read, or 2 lines really. You create a connection to the service, and you call execute, and you pass it the data. This example, it's not clear from the way I've organized the Jupyter Notebook, but it's literally the same data structure we used for the local prediction. Okay, that's going to get translated obviously to JSON because we've set up a REST API to do that. And you can see if I'm lucky in the previous run they were both the same. I'll keep my fingers crossed with the live demo, and I get a warning about credentials, but otherwise we get the same value. I'm comparing the local prediction pipeline.predict. Recall that I have an Scikit-learn pipeline, and I'm then calling cloud prediction and grabbing that out of the cloud. Very fast, low latency response times. You can see that, well, it happened to still be up, but if it had scaled down to 0, that request would have taken a little bit longer to bring up the servers, but it's very fast. Okay, so let's move on to the next section of the talk. So that's prediction. Like I said, the premise was you have a model. We combined Scikit-learn features like pipelines and XGBoost as the underlying model. You can use any of the models that Scikit-learn has to offer, any of the transforms that Scikit-learn has to offer. Essentially a click of a button, and we're working on a GUI. I think it's close to being implemented, where it's literally a click of the button. You point to the model, and you're off serving in production at production scale. And you don't wear the pager, I do. So let's talk a little bit about MLOps. This asterisk ops, if you will, is sort of a buzzword in the industry. You've got DevOps, you've got data ops, you've got SciOps, you've got I don't know what other ops, right? So of course there's MLOps, because why not, right? What do we mean by that, though? I like this diagram. If I hadn't have stolen it from a paper from some folks that work here at Google, I probably would have chosen a little different boxes. But I think it serves to illustrate the point very, very well about what MLOps are. If I can direct your attention to that teeny box in the center of the screen, that's the ML code. That's the code that you guys write as part of your job to get a model running. All the other stuff is what it takes to serve, not just serve, but to train and use ML in a production scenario. Sure, if you're just fooling around like for a research paper and you gotta get a more accurate model than the last guy that published a paper in this domain, you don't need all this stuff. You can do it in a Jupyter Notebook. Go use Colab or Kaggle kernels or your favorite Jupyter Notebook and get it done. If you're gonna do something in production, there's a lot of work that goes into it. You guys are probably very familiar with the data collection phase, maybe configuration as well. Obviously feature extraction in a production system that has to be running. It's like a service that's running on a continual basis. We have your serving infrastructure, which we already went into slightly more details about how complex that can be. You've got to have resources, monitoring, blah, 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 blah. There's a lot that goes into serving in production. So what is, when you think of the term, define the term MLOps, when you define the term DevOps, it is bringing software development, it's merging software development processes with software operation, right? So I actually think that definition does not hold up for MLOps. Why? Because I feel like we should be taking the ops out of ML. so that our jobs in serving production systems is more like the small black box and less like everything around it. Let's let the infrastructure, let's let somebody else have the job, let's let somebody else carry the pager type of thing. And so that's really our goal. So let me give you an overview of what I think the steps should be for ML ops, most of the ops taken out of the ML ops. The first step is to develop your model. I would hope that that would be 99% of your time. You spend the 3 weeks to get the best darn model you can out of your data, and then you're ready to use it in production. Of course, this is the nice GUI that I said that's not quite there yet, but it will be in a few weeks. You click a few buttons and you deploy it. You can go, and I forgot to do this. Maybe if we have a chance, we can go back and look at it. But we have monitoring and logging for all those models that we just deployed. Single click and it's all there. So you're looking at it, you're looking at your latencies, and you say, oh wait, why is my latency so high? Okay? And then you say, oh, I get it. I didn't have enough cores, or I didn't have enough nodes to handle the spikes that we had. You make a few tweaks, you click a button, and you're off and going. So yeah, maybe and ideally you don't even have to do this, but the reality is we're not quite there yet. So you have to do a little bit of tweaking, but you can even do it yourself. That's how easy it is. And that's how I think ML ops should be done. So why cloud? Now I don't know, I probably should have asked a question. I don't know how many of you, well, let's just do it. How many of your companies currently use the cloud for any of their ML? We have a few, but not many, right? And we find that to be true. I'm not here to sell you on cloud. It may sound like it, and I apologize if that's true. Obviously, that's what I do for a living. But let's just have an open conversation here. The cloud isn't necessarily for everybody. I had a few conversations offline with some people. But here's where it does shine. And if you fit these needs, you ought to consider it. We have world-class networking and infrastructure here at Google. We really pride ourselves in that. So you can count on lower latencies, faster startup times, and things than you'd get by rolling your own solutions. Elasticity and scaling, those are buzzwords as well. But if you think about it, if you purchase a cluster of computers to put in your own office or your own data center, you have a fixed cost. And if you use more than that, you're going to get really bad latencies when you're serving because you don't have enough capacity. If you use less than that, you're wasting money on servers that are sitting idle, or worse, using power. So in the cloud, you're paying for what you use. You scale up, you pay for what you use. You scale down and you're not using any, you don't pay for anything. High availability, Google prides itself in this. And part of that's due to the next line, which is Google SREs. SRE means Site Reliability Engineer. You may have heard of this. Google hires the very best engineers that know how to run and maintain production systems. And they help design the system so that there are fewer outages to begin with. And when there are outages, it's their pager that goes off. And they know how to respond and quickly mitigate any problems that are there. And that's part of the reason why Google Cloud has high availability for its services, is because of these folks here. Speed of deployment. You saw in 90 seconds, we went from a model that I trained on my laptop to one that was serving at production grade. Okay? And then you'll probably see this line. Maybe I overemphasize this, but I really believe that the total cost of ownership and paying for what you use is a real benefit of the cloud. So what if you're not ready yet? There's many reasons why. Maybe these use cases doesn't fit your scenario. Maybe your company is really slow at adopting things like cloud or other technologies. Or maybe you guys are just onboarding, but you still have a transition time. I'd like to refer you to Kubeflow, which is built by our team, the Cloud AI platform. And what it is I like to call it the anaconda of ML. So it's a bunch of packages that bring you ML, make ML very easy to do on Kubernetes. So if you guys are already using Kubernetes or thinking about Kubernetes, where you can run it on your laptop with Minikube, where you can run it on your on-premise if you have like private cloud or on-prem servers, you can run it on the cloud. Amazon just released their Kubernetes, Microsoft does their Kubernetes, but obviously I want you to use Google's Kubernetes engine. And there's the hybrid case, where maybe you do have a data center and it's at capacity, but when it goes over capacity, you can spill over to the cloud. And of course, the Cloud ML engine that I'm focusing on more or less today, I'd like to think of Cloud ML engine as managed Kubeflow. So if you don't want to manage the stuff yourself, you can pay for the managed service. All right, so I focused a lot on prediction, but the ML ops stuff is a lot more than just prediction, as we saw in the diagram. So now I want to talk a little bit about non-prediction cases. And there's a lot I can say, and I can tell you just as a teaser, expect a lot from Google in the coming months in a lot of really cool stuff, and that's all I can say. But when might you want to train in the cloud? These may seem obvious, but let's take a second to talk about them. In the cloud, you can get really large machine types. How many of you guys have 96 cores sitting under your desk? If you do, I want your machine. I can't remember what we cap out at, but I think it's somewhere like 1 terabyte of RAM. We have machines that have that much memory. And you know what I found? I actually had an intern do this last summer. I said, hey, go grab the Criteo data set, go get as much RAM as you need, get a VM with as much RAM as you need, and train it and see what happens. It took 3 hours to train. He needed a lot of RAM, hundreds of gigabytes, I think. Took 3 hours to train, and he was done. He didn't have to go figure out how to do distributed training. He just had to pay for 3 hours of a server, a fairly reasonable price with that much RAM, shut it down when he was done, and he had a really great model because it was trained on all that data, right? Number of cores. Imagine you're doing hyperparameter sweep, grid search, or something like that, and you want to do it in parallel, but you don't want to set up a Spark cluster, or you don't want to maintain any of that. Go get a machine with 96 cores. You can run 96, well, it depends on how many cores each job's running, but you can do a lot of stuff in parallel with 96 cores. Of course, you don't want to go get a VM and do all your work on that because you'd be paying for it the whole time. It's expensive. But this is what the cloud brings to you. I talked about distributed training. It is non-trivial. If anybody's had to set up XGBoost to do parallel training on Spark, you can do it. There's some sample code online to try and do it, but it's actually non-trivial. And we don't yet support XGBoost distributed training, but for TensorFlow, it's very simple to do distributed training. If you're using TF Estimator, you literally have no code to change. You submit it to the cloud, and it scales up to the number of servers you tell it to scale up to. And hopefully one day we can bring something like that to XGBoost. We have a hyperparameter service called Hypertune, which is available for XGBoost and Scikit-learn models. And it gives you much better results than doing grid search or random search. It's state-of-the-art algorithm, so you'll get best-in-class performance there. And it's all in parallel. You know, so you don't have to wait over, you don't have to. So I talked to a researcher here at Google, and he says what he does is he plays around during the day on small data sets, gets things how he likes them, sends off a job at night, comes back in the morning and checks on how well his model does, keeps his fingers crossed that there was no errors halfway through, right? Anybody relate to that? I know that's what I did during my PhD too. Repeatability. So what I mean by this is, I think there's more examples, but the best example of this is with continuous training. So we're talking about training a click-through rate model where you get new logs and tons of them every single day. And every single day you're going to train another model, right? And so you're going to use the same code, and you're going to use it every single day. Or actually, a lot of people train like every hour, so they're training very frequently. You're not going to want to go to your Jupyter notebook and hit a button at 4 p.m. every day to train another model, right? This is a repeatable process. It needs to be productionized. It needs to be robust. And so the cloud is really great for this. And in fact, if you're taking advantage of those large machines and those large cores, you know, it sends off a job. It uses all those things for a short period of time. It shuts it down, and you only pay for that time that you're doing it. So let's come back here to see what that might look like in the cloud. So there is a price to pay when you're switching from your local machine to the cloud. You do need to package up your code in a way that the service can understand. And there are multiple ways to do that. We'll be supporting containers, which is becoming an industry standard way to do it. For now, we use Python packages. So you just run this, you just run python setup.py sdist. You see the second command then uploads it to a bucket in the cloud. And I think that's finished. And then I'll go ahead and hit enter. And then you can see right here, all I'm doing is saying submit a training job called CTR for click-through rate with the timestamp so it's unique. I'm saying that it's trainer.train. This packages is what we just uploaded. The runtime version tells us which version of. Now that's a little. I wish that it was more obvious that this was like scikit-learn whatever version, but this does translate into scikit-learn version. This is Cloud ML Engine's runtime version 1.8. We're going to do it in US Central. It's with this project and a few command line parameters. So just since I forgot to say this train.py is that exact code we saw at the beginning. The only thing is like you would probably take off that max sample lines that I had because my Pixelbook couldn't handle it, and it took me, I won't admit how long it took me to figure out that's what was crashing on my notebook. because it didn't tell me. And you might change the max depth or the number of estimators to be what you would have in production. This is your actual production code. So you make a few tweaks, you send it off to the cloud. You can see that the job was queued. Again, we don't have a first-class integration, so we have to go over here to our list of jobs. And let's see, that one, you see the spinny thing means it's still spinning up the machines. This is training. Our prediction service actually spins up the machines very, very fast. The training takes a little bit longer. I think if it's a single machine job, it's usually around 1 or 2 minutes. So we can go to this job here, take a look at the logs. Nothing super interesting, just to show you that there's this integration here with the logs if I'm lucky enough to get it to come up. So you can see that all the output's captured in the logs in case you need to go back and figure out something that's wrong or something that's right. And you can see that the job completed successfully. Okay, so that's how you send off a single job. But the use case that I was talking about is really about productionizing this and doing it on a daily basis. So there's how many of you are familiar with Airflow by chance? A couple of you are, probably the data engineers, I think. I mentioned to somebody before we started, I'd hint at a little bit of pipeline here. So what Airflow is, and there's lots of orchestration systems, but it allows you to run, chain together various processes that you can then do on a repeated basis, in this case on a daily basis. And so you can see that right here. And I'll get into what this actually means, but you can see that every day for the last 2 weeks, this model has, that code that we just submitted to the service to run to train a model, has run on the previous 7 days worth of data, produced a model, and then pushed that model to serving. So let's go ahead and, you can see that in a graph view here. Very, very simple DAG. I did that for the sake of this demo. It just does training and create version, but you guys have already pointed out an obvious problem with that. If something went wrong during training and I pushed it to production, I'd be in a world of hurt. Could even get fired for that. So what you would normally do, and it's not too much, it's actually not that difficult. You can put another node in the graph that runs evaluation and another node in the graph that checks that the quality of that model is better than the previous, or the model that's currently serving before you push it, and then go ahead and push it to serving. But for simplicity's sake, I just trained and pushed. And you can look at the code to do that is actually very, very reasonable here. Again, you have the preliminary, which binary do I use, etc. These DAG args are just necessary for Airflow to work, a little bit of overhead, copy and paste is what I like to think of it as. And then here's where you say, hey, with DAG, in other words, with my pipeline that I'm trying to define, you have this training op, which looks very close to the G-Cloud operation, but in Python code. It says, hey, use this binary for training. And then you have the create version op, which again looks like the G-Cloud option for pushing a version. So I don't know how many lines of code that is, but the core of this is what? 20 lines of code maybe? And we've defined this pipeline that we're able to run in the cloud on a daily basis that pushes the models to production. Let's see if I have this. So you can see, here's the model CTR daily. Remember how I said models like a container for versions? And here are all the versions of that model that got pushed on a daily basis. Now, also in a production system, you'd probably be garbage collecting these, so you didn't have so many laying around. You can see that this is the default one. So if I send traffic to this model, it's going to actually go to that version. You'd want to update that on a daily basis, at least after you'd validated it. So, yeah. Any question? I forgot to say this. It was kind of difficult with all the interruptions we had. My preference was going to be to have questions in line, but I'm almost at the end of my talk now. But any questions about these pipelines or the training? Yeah?
The logging that you showed,
Yep.
is that something to spit out with a cloud box itself, or is that something if I had logging in my code that I can spit out to?
Yep. Yeah.
Both?
So if you do your print statements, your logging.info statements, if you're a Python programmer, those things show up here. And I think it tells you which one's which. The standard error shows up as, unfortunately, as orange warning signs, but because there's nothing to be worried about. That's just XGBoost telling us that it's doing work. Any other questions? So this is really the end of my talk. Just to summarize in a few points, productionization is hard, cloud is easy, and you pay for what you use on the cloud. All right, and a few teasers, I guess, before we move to see if there's any other questions about the entirety of the talk. But our team is working on increased focus on reducing MLOps. So we saw probably 10 boxes on that page, and I addressed a few of them, like the continuous training case and the serving case, but there's actually a lot more boxes on there, and you better believe that we're spending time making this easier and easier as time goes on. Increased cost efficiencies. That's a continuous focus for us. Because we're able to amortize the cost of the infrastructure across everybody, so we're actually able to get you lower costs than you might on your own. And then we're also working to allow data scientists like yourself, and even data engineers as well, to share their reusable work with others. We're working on ways to do that.